Welcome back to our second class in this series, Smart Contract Basics. So smart contracts are written in Solidity. It has a similar syntax to JavaScript, but it's not exactly the same. But if you can write JavaScript, you can probably write code in Solidity. The variables have to be declared by type. So in a lot of programming languages like JavaScript, you just type in var, and that's your variable. In PHP, you just put a $sign in front of it, and that's your variable, and so on. But in Solidity, you have to actually declare what type of variable it is. Solidity has different libraries in JavaScript, so while it's similar, certain things act a little bit different, and Solidity uses different error handling than JavaScript. And each contract in Solidity has to be limited in size. So where you could write like 100K of code in JavaScript and it work just fine, you have to break that up into multiple contracts in Solidity. In this series, we're primarily going to use Remix for editing smart contracts and going through them. So to get to Remix, we're going to go to thetascan.io, go to Smart Contracts, and then click on Remix for Theta. It'll take a minute to load in your web browser, and this will give us an environment where we can write a contract and we can test a contract, and you can technically even deploy it right in Remix or on Thetascan. So to get started, right here is a list of contracts that we'd have available to us. I have an example in there. The next tab down, you would compile your contract. So after you select it, you can use different compilers and compile them, and then you can deploy it and test it right inside of the web browser without accessing the blockchain. Now this also gives you the ability to inject it right into the blockchain if you would like. In Solidity, there are 6 main variables that you're going to use. The first being a boolean, which is simply true or false. The next will be an int or uint, and that has 256 bytes in it. And you can specify exactly how many bytes are in your int or uint. So you could say that my uint has 8 bytes, and that'll limit the size of the number that's allowed to be in that space. The next will be an address, which can be any Theta address. And if you want them to receive T-Fuel, you need to make sure the address is payable. So you just put the word payable after address. And then we're going to do bytes. And then the next variable is enum. And an enum is a state. So like you pre-select the state. So the state could be like pending, paid, or canceled. And then you have to choose one of those 3 states. And then the last variable we're going to use is a string. The next thing we need to look at before we start testing this and using Remix is we need to look at public versus private variables. So if you create a string and you put the word public after it, Solidity will treat it like a function where hello world will always pull up the string. If you create a string and don't put public after it, Solidity will consider it private, and hello world, nobody will be able to access the string value that's in it. And the same goes for uint 256 decimals. So this is a number and it's 18, so decimals equals 18. If it's public, then anybody can search decimals down here, select a function, decimals will show up as a function, and they'll return 18. So this decimals won't exist. If you have public after it, decimals will exist. Now let's take a look at this and try it out. Now let's test out what we just learned. So I have a quick example right here. We're going to open it up. And all smart contracts has to start out with the version of Solidity you want to use. So I'm using 8.7. And then you're going to have a contract, which I named my contract. And then I put a string in here, which is public, and the string's name is welcome. And then I said hello and welcome to Theta. And then I created a function where we can send a new string and then change the welcome. So we have our contract in here. We're going to go over to the side and we're going to compile it. And you want to make sure the compiler is set to the version you're using, which is 8.7. We're going to compile example. And then it's going to show up with any errors or warnings here. So it's giving me a warning that it doesn't have a license at the top of it, which is fine for testing. If there was something wrong, like let's put a number in there and I'll compile it here. It's going to say that, hey, it's red. You'll get a red exclamation point and it found something wrong. And it's because I put a 3 after function. So let's recompile this. So now it's compiled, and when we want to test it, we're going to go down here, and now we can deploy it. So we have my contract on my example sol, and we're going to click deploy, and then down here where it says deployed contracts, we can test it out. So if we want to read welcome, and read welcome's completely free, hello and welcome to Theta. And then there's debug data down here, which you can look at and read through it if you need to, if something doesn't work the way you expect it to. And we can change what we want welcome to say. We can make it say, this is an amazing day. All right. And we'll change it. And then when we pull it back up now, it says this is an amazing day. And that is how we can write a contract, quickly compile the contract, and then test it out right here. Before we go any further, we needed to take a deeper look into strings. So if the string is declared in the main part of the contract and you're storing it on the blockchain, you will declare it as a string and then the name of the string and then what it equals. And then you can make it public or private. If the string is being used in a function, for example, you're passing a new string into the name, then you're going to use string memory. You have to put the word memory in there. And then the name of the string equals whatever you're doing. So for this example, string memory, my string equals name would make my string equal to my token. The last thing we need to look at is enums. And this allows the user to specify the state of a specific variable. So only what you predefine it as can be put into it. So for an enum, it can only be pending, shipped, delivered, and canceled, if that's what we make it. So in the contract, we can pull up an order and say it's order number 55, and we can see what state it was last put into. Was it put into shipped? Was it put into canceled, pending? And these are the only statuses that can be in there. You can't give it a status of unknown. Now let's go back to Remix and test out public and private variables. So we are going to create a new function and we're going to call it return welcome, and it's going to be a public view that returns a string from memory. And then we're going to simply return welcome. So in this function, we're just going to return the variable welcome back, and it's storing it in memory. So up here we did string public welcome. Here we're simply going to do string from memory, and we're returning the string welcome into the function. So we're going to compile it, and everything's good to go. And then to keep things simple, I'm going to delete this previously deployed contract, and we're going to deploy the new contract. And down here, you're going to see where you can click on the variable welcome, and it's going to return it. Or you can click on the new function we created called return welcome, and it's going to return the same public string. Now, if we don't want welcome to be there and we only want to use the function, we need to come up here and we need to remove the word public. And I'm going to delete this deployed contract. And then we are going to compile it again. And then we are going to deploy it. And you can see that the string welcome is no longer a function, so we can change it or we can return welcome. We only have these two functions available to us. So if we want to change it to today is great, we would change it. And then when we return, it returns today is great instead of hello and welcome to Theta. Let's further dive into our example here. So let's add a number. So we're going to enter a uint 256, and it's going to be public, and we're going to call it number. Now if we want our function return welcome to return this number, and let's make it 500, we will change string memory to uint 256. And you can also specify exactly what you want here. So you could tell it to return number if you want it to, and then you could delete this and the function would just always return this number. But if you want to put it down here, you could also put number here and just put return a uint 256. So when we compile this and we go over here and test it out, and we're going to click deploy, and we're going to see that our number is 500 because it's a public number, and we want to return it. It's going to return 500 in our function. Now that we've taken a look at how variables work in Solidity, we need to jump right into arrays. And how arrays work in JavaScript and how arrays work in Solidity are totally different. So this is the biggest difference, in my opinion, between Solidity and JavaScript, are how arrays function. So I hope you guys are ready. So while Solidity does have arrays, I have never ever used them in any contract that I created in this form. So you can create an array, and to do it in Solidity, you'd have to create an array of addresses, an array of numbers, a uint, or an array of strings, for example. So to create an array, you would say address, and put the brackets in there, and then name the array, which would be my addresses. If you want it to be a uint, you'd put your brackets in there, and then make it a public my array. And then to add to the array, you simply create a function, add element is the name of the function, give it a uint value, so what are you sending to it, and then public, and then you would say my array, and you're going to push a value in there. So it's going to push whatever value you send here into the array. Now, the biggest problem with this is if you put 1,000 values in that array and then try to go through it, you are going to max the gas out in the contract and it won't finish. So if you use arrays in this manner, it's highly, highly likely, if there's more than like 5 or 10 objects in the array, that it'll be too expensive and you won't have enough gas in the contract to properly fulfill the function. So I would highly recommend staying away from this unless there's a specified need to use arrays in this manner. Now, mappings you are going to use a whole lot more, and it's probably the most useful tool you have available to you in Solidity for arrays. And what mappings are is they basically create a searchable array. So it doesn't use up all your gas, it quickly finds the information you want. So in a mapping, you create the variable by calling it a mapping, and then what type it is. It's an address that returns a uint. If you want it to be a uint that returns a string, you would put that here. And then this is going to be public and balances. So the name of the mapping is balances, and you're going to send it an address, and it's going to return to you a number. So in this quick example, we created the mapping, and now we want to update something in the mapping. So we call it function update. We're going to send an address as an account, and we're going to send a number as a new balance, and it's going to be public. So we have balances, we send the account, which is the address, and that account will then equal the new balance, the number that we're sending. So when we search for the address in the mapping, it's going to return the new balance after we update it. And you can store anything in your contract in this way. So for example, if you need to have like 5 searchable items in your contract, you can have 5 different mappings, and each one will return a searchable item. And the last aspect to arrays is a structure. Inside of a struct, you give it a name, and then you can put data in there. So you have your mapping, and then if you want it to be multi-dimensional, like have many different variables inside of a map, you could put a struct in and then tell it to how the data is formatted. So in this example, we're going to do purchases, and we're going to ask for an address, and then the amount they paid, and then the invoice number. So if we want to map to order number 5, and we want that to return us an address, an amount, and an invoice number, you would use a struct. So you would just simply map address to purchases, and then you'd put all this data in, and you'd send it through when you run your function. And this is how you would create multi-dimensional mappings inside of Solidity. Let's head back over to Remix and give this a test. So we are going to delete this. We are going to create a mapping, and we're going to say a uint 256 is equal to a uint 256, and we're going to make it public, and we're going to name it invoices. So what we did here is we just created a mapping, and I said a number then returns another number, and it's public and it's invoices. And then we're going to come down here, and we are going to call this update invoice. And then we are going to need to send it to uints. So uint 256, and we're going to call this invoice number. And then we're going to send it another uint, and we're going to call this one amount. And then we are going to come into the mapping and say invoices. That's the wrong one. And we're looking for invoice number equals amount. So to recap, we created a mapping for a number that returns a number in invoices, and then we created a function where we can update it, and we're going to send an invoice number, and then it's going to return an amount. Now in Solidity you can't use decimal places. So if we wanted to use decimal places, I'll show you that in a second. And what this does is it does invoices. We're sending the invoice number and we're returning the amount. Let's compile it. And there's no errors, so we are good to test. We're going to delete and clear out our deployed contract. We are going to deploy this one. So you have our contract, and we're going to open up our functions here. So we're going to send invoice number 150, and we're going to put in the amount is 800. And we're going to send that. So now if we call 0, it returns 0. If we call invoice number 150, it returns 800. And if we want to update this with the same function, we didn't set it up a way not to, we could put in 900, and when we call it, it'll return 900. Solidity does not use decimal places. Everything has to be in whole numbers. So when you want to use a decimal place for data, you have to do it on the DApp side of things. So you would use it in the JavaScript or the Python or the PHP, whatever code you're using to interact with the blockchain. That would simply multiply the number by 100 if you have decimal places for money. If you have a bunch of decimal places, you can multiply it by like 1,000, and that would give you 4. And then when you pull the data out of the blockchain, you simply divide it by 100 or divide it by 1,000, whatever number you multiplied it by. And that's how you would store decimal places in the blockchain. And that wraps up arrays. So in a nutshell, to recap, arrays really aren't used in Solidity very much. You can use them, but they can't be huge. Mappings can be as big as you like, and they are heavily used. And to create a multi-dimensional array, you'd want to use a mapping with a structure, with a struct. Next, let's look at different functions. So we have different function types. They can be internal or external, very much like a variable can be public or private. You can name it public, or it can just be used by the contract. And there are 3 different types of functions. Let's start with pure. A pure function means it doesn't really do anything with the blockchain. It's simply for like adding or doing something very minuscule on your contract. So if you wanted to add 1 plus 1 and always return 2, that would be a pure function. A view function is going to pull some sort of data off of the blockchain and give it to you. So if you want to create a function to retrieve data from your contract, it's a view. Anybody can run a pure or a view function if it's public in your contract. And the last function type is payable. Payable generally means you're going to write some sort of data to your contract. So payable functions are, I want to update a number on my contract. I want to change a balance. I want to transfer a token. I want to do something. I want to change the state of an enum. So that would be a payable function. And an amount of T-fuel has to be sent to the contract for the contract to update. So the basic layout of a function in Solidity is you have your function, you call a function, you send your parameters through, you determine if the function is internal or external, and then what type of function is it? Is it pure? Is it a view? Or is it payable? And then it returns some sort of data. And on payable functions, you don't return any data. It would just simply be on pure and view functions, you return data. Next up is error handling in Solidity. And error handling usually has to do with receiving value in your contract. So you have 3 different types of error handling you can do. You can require, you can revert, or you can assert. And for this class, we're just going to go through require and revert. So to require something, let's say you want a contract and you want somebody to send you an amount of tokens that is greater than 0. So if they send you 0 tokens, you want it to fail. So you would simply put in the contract require, amount is greater than 0, and then a comma, and then your error message, and then close the parenthesis. Now, if you want to explicitly tell that contract to that function to fail or not let it run based off some sort of data in your contract, let's say you want to have 100 T-fuel sent to you, and if the amount is less than 100, you want it to fail and revert. You would simply put in if amount is less than 100, revert insufficient funds. So it's going to give the error message of insufficient funds. And that is how you handle error handling in Solidity. Next up, we have contract size. The maximum size of a contract in Solidity is 24 kilobytes. Now, if you're writing a big contract, and your code is over 24 kilobytes, let's say it's like 30, you can use code optimization to shrink down your contract even further, but it comes at a cost that is harder to decompile. So it's optimizing your contract, but if you have to ever use a decompiler to look at it and see your contract for some reason, it's making it harder to do that. But it is available. The next thing I want to look at is multi-contract design. Since you can only have 24 kilobytes in each contract, you can design multiple contracts to interact with each other. When you're doing multi-contract design, you want to design it in such a way where one contract flows into the next contract, and then that contract flows into the next contract. If these contracts start returning data back, then you could get into a attack vector or a hackable vector in your smart contracts that could pose a risk. But if they always send data downstream, then you limit that risk greatly. The next thing we have are proxy contracts. So proxy contracts are where you create a very simple contract at the start that your DApp will call. And then that proxy contract simply sends the information to your payment contract. So you just put in here, call this address, and this is the address of the payment contract. So the proxy contract gets called, the proxy contract calls the payment contract, and then you get paid. Now, down the road, you say, hey, my payment contract is obsolete or gets outdated, or I need to update it, or I need to do something. With a proxy contract, you simply take the proxy and point it to your new payment contract. The old payment contract stays on the blockchain, but the proxy contract uses the new payment contract to accept your payments. So your DApp still points to the proxy contract. It's just the proxy contract points to a new contract. And this is a way to update your contracts on the blockchain. And finally, we've reached security. Smart contract security. There's a lot of different attacks that can happen to your smart contract to try to take funds out of it or exploit funds. In this class, we are going to go over reentrancy attacks. So what a reentrancy attack is, it exploits a vulnerability in the smart contract when a function makes an external call to another contract or updating its own state. And basically what it does is it allows someone who's maliciously acting to keep entering the function over and over and over to do something like withdraw funds from it before the state is changed. And this allows an attacker to possibly drain all the funds from a contract. So let's go through how a reentrancy attack works. So how a reentrancy attack works is you have your payment contract over here, and then I create a new contract that I call my contract. It pays your payment contract 10 T-Fuel. And then I claim a refund in my function on my contract. And in that same function, I claim another refund. And then I claim another refund. And then I claim another refund. So I paid you 10 T-Fuel, but I'm claiming 40 T-Fuel back. And before the function completes, it then sends me 40 T-Fuel back, and I just made 4 times my money in a refund. So it's basically calling your refund function 4 times. And because your refund function didn't change the state in the contract before it refunded me the money, I can keep doing it and doing it and doing it. And maybe I do it like 100 times to get 400 T-Fuel back. And so when you're thinking about security, you need to make sure that you code your contracts in a way where they can't re-enter it, or you put no reentrancy guards in place in your smart contracts. Finally, let's take a look at a couple free smart contract auditors, Slither and Mithril. Slither, you're going to install on your Linux machine, you're going to put your smart contract into it, and it's going to process that contract and kick you out a nice report. That report's going to have errors and warnings, and then you can go back and fix your errors and warnings. Mithril is going to do very much similar. You're going to install it on your Linux machine, you are going to put your contract into it and your bytecode, and then it's going to process that. Now, Mithril takes much, much longer, sometimes up to hours to process a smart contract, and then it's going to kick you out a very, very similar report with any errors or warnings that it finds. Both free smart contract auditors are looking for vulnerabilities in your contract, and they're great for new people starting out that are just coding, so you can see where you made a mistake. And free smart contract auditors may not be for every project, but in this course we are going through how to write a contract and how to audit it. If you're doing a larger project that needs more audit support, or you're planning on running a lot of money through it, then it is always worthwhile considering one of the several smart contract auditing firms that are out there. Thank you for watching this class. We went over the smart contract basics. I hope you've enjoyed it. In the next class, we are going to go through how to launch a TNT20 token on the blockchain and an NFT token.